right, I decided actually literally this morning to abandon the remainder of the lectures on the sparse models. So at least we cover something on infinite Gaussian process, because at least two of you demanded that. Okay, so now the sad story is, at some point I had prepared like 400 slides with topics that they were a little bit more advanced than what we will cover today, and I cannot find those slides. So even if we wanted to have more lectures, I don't know where they are. So, all right, so we will talk a little bit about Gaussian processes for regression and also for classification, and maybe that would be a good way to finish the course. Okay. I don't know what, I don't remember what software you use for doing the homework, but there's plenty of software out there, and both in Linux and Matlab, and the one in the past that students had used is this GP software coming from Sheffield by Rasmussen and Williams and others. And there is a very nice link and lots of tutorials. So if you read those papers, you can actually download also the data used for each example, and very easy to run. And there is sort of semi-complete Linux version of this software as well. So what's a Gaussian process? A Gaussian process, in a trivial manner, it's a generalization of a multivariate Gaussian distribution to infinitely many variables. Literally, at the end of the day, all the calculations we will do in the computer, they're calculations we do for a multivariate Gaussian. But GP is a little bit more than a multivariate Gaussian, because when you think of a multivariate Gaussian, right, with many variables, you have no idea what that means when you say push this to infinitely many variables. So what exactly that means? So a more formal definition of what the GP is: a collection of random variables, any finite number of which have Gaussian distributions. Okay? So you can think sort of having many variables, and if you take any subset of those, they actually follow a multivariate Gaussian distribution. Okay? Really, for us, a GP is a probability model over functions. All right? So we will model distributions over functions, and that's what the GP is all about. Now, in many ways, to motivate the GP, you can start with the standard regression models that we have seen in the course, and I'm giving you here the regression function, right? Linear model where the input is mapped to some future space phi of x. If you think about it, what we did in the early lectures in the course, we put a prior on W. So if you make a probability model for W, in essence, looking at this equation, even with a finite set of basis functions, this results in a probability model for Y. And you can think of a Gaussian process coming that way. Of course, we're going to try to generalize, because when you look at this equation, if you think of that this equation generates a probability over Y, in some sense, you are limited in your view, because phi are a given set of basis functions. And the approach we would like to follow is one that has infinite sets of basis functions, or in principle, no basis functions at all. Okay? But somehow, you'll be able to reach some equivalence between the classical regression model and Gaussian processes, and we will do this in the lecture today. There is, if you search in the literature, there is many names for what a Gaussian process is. So people in geostatistics, they call these Kriging models. And also, you know, many other things that you think they are irrelevant, like radial basis function networks, Kalman filters, etc. You can actually write all of this in an equivalent Gaussian process form. So the concept is sort of generalizing many ideas that they're out there. All right. So let me see how what we learned with regression models can actually allow us to generalize this to Gaussian processes. So, so we start with a regression model that I had before. We have a bunch of input points x1 to xn, and this regression function results in a joint distribution of y at x1 up to y at xn. And I can write all of these values of y as a vector, a bold y being the design matrix phi, or x the way we had seen it in some lectures. You know, I'm using here design matrix phi because I don't operate on x, I operate with this future space phi. So design matrix phi times w. Now, it comes out that if you take w to be, I mean, the earlier models we took w to be a Gaussian centered at 0 with a covariance or a precision alpha. So in that case, you can show that this vector y follows a Gaussian distribution. So you can see here, if you take the expectation of y, you get phi times the expectation of w, which is 0. And if you take the covariance of y and you use the equations for how you transform covariance, you can write this phi times E of w transpose, phi transpose. And this is the covariance of w, and the covariance of w is 1 over alpha. All right? You remember in the primitive model we used, we took that all the w's had the same precision alpha, so covariance 1 over alpha. So effectively, in our old model for regression, if you take all of these n variables together, they have mean 0 and a covariance that is phi transpose. And if you actually write this explicitly component-wise, the components look like phi of xn transpose, phi of xm, scaled with 1 over alpha. And you remember when we discussed kernel methods, literally what we have here is the inner product of phi of xn with phi of xm. So this is a Gram matrix, all right, defined in terms of this kernel function that you see here. So what we have done is to derive the distribution of y, which is a Gaussian, using only the distribution of w. We have shown in the slide that the only thing you need is to know this kernel matrix, all right, k. And then the question that someone can pose is, if the only thing I need is this kernel matrix, can I generalize this where I don't really use anymore the basis functions phi of x, but somehow I start directly with k. All right? So if you define this kernel here, independently of basis functions, the same equations will hold, right? So the distribution of y will be Gaussian, and effectively what you now have is you're going to have a distribution over functions, in this case the regression function. But you can do this without following this methodology. You can go basically and say, forget these basis functions, I'm going to postulate k directly, and there is the distribution of y. And you notice here, in essence, these points n are arbitrary, right? You can take anything you want to, and this is basically what is going to allow us to generalize and call this a Gaussian process, because any subset, any points x1 to xn, when we compute this joint distribution of these y's, it leads to a Gaussian distribution. All right. You notice something interesting, that to describe the distribution of y, the only thing really you need here is the covariance, that kernel matrix k. The mean, you know, in this particular case came to be equal to 0, but the only thing we need is second order statistics here defined in terms of the covariance. So if we want to come up directly with the distribution over functions, you can introduce this kernel. This will define the covariance matrix, and there is the distribution of y. Okay, so let's compare things with a multivariate Gaussian. So y follows a multivariate Gaussian. This is our standard definition. So for a GP, think that the indices of y become continuous. All right? That's why we say once we have a GP, for any joint arrangement of y's drawn out of this continuous distribution, so the indices will become continuous, okay? And instead of the mean function and this covariance, instead of the mean vector and the covariance matrix, now we're going to have a mean function and a covariance kernel. And if you take the joint distribution of f of x1 to f to xn for arbitrary x1 to xn, basically what you do get is you get a multivariate Gaussian that looks like that, okay? So the key ingredient here is that you can draw these values of f of x1, f of xn for arbitrary, basically, values of x1 to xn. And when you take the joint distribution, it looks like a multivariate Gaussian. But we derive this by assuming that there is a mean function and there is a kernel function, okay? And this is what will define a Gaussian process. All right, so what, if we don't use basis functions, right, you're going to have to assume something about the kernel. And the most famous kernel for Gaussian processes is the square exponential kernel. So if you have a vector x that lives in d dimensions, you can define a kernel like that. So this is the strength of the kernel, and these are the length scales for each direction. So basically, you need this because maybe the functions that you try to represent very differently in each direction, maybe in one direction faster than the other one. So these length scales will be able to capture what's going on. Now keep in mind, if you try to model a function with a square exponential square exponential kernel for the GP, you don't really a priori know what these LIs are and S squares. So somehow you will need to learn those. All right? I mean, you may have some prior knowledge, but in reality, the only way you can figure out what is going on is to have some training data and then try to compute what these parameters are. So we will discuss a little bit later on this thing. So here are various plots of this square exponential kernel. I try to fix all the links. So if you click the links, hopefully will open a little functions that you can see these things. So these are the square exponential kernel for different strengths and different length scales. You can call this a Gaussian kernel, and in this case, you notice the length scales are the same in each direction. These are samples from a Gaussian process with a square exponential kernel. You can see the variability that you get. And here is another kernel that has lots of applications, actually, okay, that we will not see today, but is used widely in time series, for example. And you can see here the variability. There is lots of oscillations. All right, that's why it's used this in time series, so you can model dynamical processes. 2D kernels. So this is an isotropic square exponential kernel with the length scales to be the same. A non-isotropic kernel, so the length scales in the two axes, x and y, are different. Okay, and you may ask now, in case you forgot, right? How are you, all these samples that I had here, you may say, how do you draw these samples? I mean, what is the algorithm actually to sample this from a Gaussian process? You remember, if you take a finite set of input points and the y's are following a multivariate Gaussian, so the only algorithm that you need to have in place is sampling from a multivariate Gaussian. So if you have the points x1 to xn and this is your covariance matrix, what you need to do is a Cholesky decomposition, compute the mean, And then you take n samples from the standard normal, and with this little transformation, you can actually get samples from the Gaussian process. Okay, nothing sophisticated. Okay, so you do Cholesky decomposition for these Gramian metrics, and you sample from a standard normal, and you use this transformation to get samples from the GP. Now, a warning notice for those who play with Gaussian processes. A lot of times, and not only during training, you will find out that the covariance matrix is not well posed. Okay, so you can think, for example, if these length scales go to infinity, all right, there's no variability in one direction, you will start getting, you will be getting singularity. If they go to infinity, actually, we will find a way with relevance determinations to get rid of those dimensions. But you can take the extreme case of actually L going to 0, and in that case, you will see that somehow the system will not be able to identify the correct parameters. So what you need to do is you need to be sure that this covariance matrix is invertible. And so there's a lot of tricks in practice to stabilize the covariance matrix, and they go under different names. The most common trick, actually, and I think the Matlab software, the link I gave you on the first slide, does this, is to take a covariance matrix like that and always add a very small positive number in the diagonal, right? I mean, we do this to invert any matrix, but that very small number has a statistical meaning, okay? But at the end of the day, the only purpose that it serves is to invert this matrix A. All right, so I give you different combinations of samples from a one-dimensional GP, small length scale and 0 mean. Medium length scale, you can see the variability is not as significant as in the previous. Large length scale, so the variability is even less here. You can play with the signal strength, and you can see the smaller the strength is, the less the samples from the GP vary. Okay, the higher the strength here, I see it's 1.5, and here is 1, and here is 1.5. Here is the same thing. The only difference is there is a mean value in the GP is non-zero. These are samples in 2 dimensions. But the way it's interesting, you may wonder how useful are Gaussian processes if the samples look to be varying too much. So maybe the realizations vary too much, but when you average, you will actually get functions that you will expect to see in your problem. So it doesn't mean because all the samples look like that, that actually what you try to model looks like that. Okay, so let's do some analysis now. So we're going to assume is we do regression, and we're trying to model a function, right, that models a mapping from input from x to y, all right? So we're trying to model this function y of x with a Gaussian process. We're going to assume that we have n observations, and so this is our function, and the observations we have include some additional noise, a Gaussian noise, that has precision beta. So basically what we have is we have a likelihood model that looks like this. Okay? So this is the regression function, and we just put some constant noise around the values yn. So we're going to assume that so the joint distribution of the observations t given the function values y looks like this. All right, so again, y is the function we're trying to learn, calculate it at the points x1 to xn, and at each point xn, basically what we observe is y plus some noise defined by the precision beta. Okay, so this is the likelihood model. P of t given y looks like this, and the x's don't appear because they're implicitly there, but they're not irrelevant in the big picture. All right, where is the Gaussian process comes? we're going to assume that the joint is that y follows a GP, and we call this a Gaussian process prior. So the joint distribution of PYs is given like this, a multivariate Gaussian, where this is a covariance matrix defined, for a given kernel. Remember, I can write this as a multivariate Gaussian even though y follows a GP, because you remember if I take a finite set of the values y1 to yn, they follow a multivariate Gaussian, right? For any points x1 to xn. Okay, so what we have is we have a likelihood model, P of t and y. We have a prior GP that defines the joint distribution of y. And if you integrate y out, so if you integrate basically the function values out, what you get is you get this Gaussian. I mean, this is a standard calculation for linear Gaussian systems. If you try to marginalize, P of t gets to become a Gaussian, and the covariance matrix of the Gaussian is the kernel matrix K plus beta minus 1i. Okay, and I remind you, beta is the noise that we put to the function to get the observations. So you know where this C is going to be very useful in our lecture today. So if you look at this equation, what is this? What's the name we use for P of t up to now in all the course? Say it again. Marginal likelihood, the evidence, right? So effectively, this is the only thing we know about our model. And so whatever unknown parameters there are, those unknown parameters we have to be calculated by maximizing the evidence. Okay, so we will come back to this problem later on. All right, and I think the slides contain the derivations of this of this formula. There is really nothing, just marginalizing the product of two Gaussians. Okay. All right. So the question is now how, so we have a likelihood model. We have a prior GP, right? We assume that the functions we try to model follow a GP with some kernel, and we call that a prior GP. So we actually want now to be able to use this model and do predictions. So effectively, you would like to know if you already have observed some data T of n, this vector is a bold there, right? So it involves the observations T1 to Tn. We would like to know at a new point xn plus 1, what is the distribution of Tn plus 1 given Tn? In some sense, we would like to compute what is called the posterior Gaussian process, all right? I mean, assuming that actually this distribution comes to be a GP. All right. So remember this vector T here, it's a ball vector, right? It involves T1, Tn to Tn plus 1. Would you agree with me that this equation is also correct? Can I write this equation? And what has been used here, you remember when I started, right? Where was it? When I wrote, so if we take n points, right, the distribution of P of Tn follows this multivariate Gaussian with covariance Cn. Can I do this? Can I write this thing? Can I say that this is also Cn plus 1? And so what is the idea here? The derivation will be the same as before, but what is the fundamental idea that allows me to write this equation? Say it again? I have not used any posterior yet. There's no posterior, nothing. So this is, I want to write the joint distribution of T1 to Tn plus 1, because really I am going to use this calculation to get this distribution, this predicted distribution. But I'm saying is, what allows me to write this equation in exactly the same identical form as before? You remember how we derived it, right? We wrote the likelihood, and then we had the prior, which was a GP. And we took that the prior of y1 to yn follows a multivariate Gaussian. To do this derivation, you're going to have the function values y1, yn plus 1, but also those follow a multivariate Gaussian because they are samples from a GP, the same GP. You remember the whole idea of GP, right? It's not like one multivariate Gaussian. Is you can take any finite set of the values of the function evaluations, if you like, and they are following a multivariate Gaussian. So here what I do is if you take for the y's n plus 1 values, and you follow the previous derivation, you get that the likelihood is given by this formula, where the metric Cn plus 1, I'm going to write it explicitly, the metric Cn plus 1 looks like this. I want you to look carefully and tell me that, you remember that metric C that I had, right? Involves the noise, all right? It involves the noise parameter, but the rest are really kernel values. So would you agree that Cn plus 1 is Cn, and then a vector k, k transpose, and C, where the vector k is this, and C is that? Look carefully and tell me what exactly is going on. Cn plus 1, right, will be the kernel metrics effectively computed at the n plus 1 input points. Now, the n by n components will be what I have for the values x1 to xn, and what this will be basically the kernel values of what? Each row will be for x1, x2 to xn, and the other component in the kernel will be the point xn plus 1. Right? Because this is for n plus 1 points. All right, so this will be what you see here, the kernel evaluated at xn, x capital N plus 1 for n 1 to n. And then what C will be, C basically will be the kernel xn plus 1, xn plus 1. And of course, you know, everywhere you add, in the diagonal, you add the noise beta as well, all right? And so Cn plus 1 is what you see there. Everybody follows what we're talking? I mean, the idea here is we are taking this draws from this prior Gaussian process. Originally, we took draws at n points, and that gave us this covariance matrix. Now we take draws from n plus 1 points. So we get the covariance, you know, we get the kernel matrix for n plus 1 points. So this part will be the same as when we use the n points, and this will be the additions, this vector k, and this constant C that you see like that. Okay, so can you tell me now, all right, so the distribution of, so these are observations, right? So this is the probability of my evidence of these observations for a multivariate Gaussian. Remember now what's my objective. My objective is to know what's the predicted distribution. If I have observed at the points x1 to xn, if I have observed t1 to t capital N, I would like to know what is the distribution of tn plus 1 given this bold T capital N, right, at the point xn plus 1. So what is the idea now? Here we have the joint distribution of all of these t's, and I want to compute that. So what calculation will you do? So we already have the distribution t1 to t2 to tn plus 1, and I want to find t of n plus 1 given t1 to tn. What calculation we will use here? If you have a Gaussian distribution and you partition it to a subvector xa and xb, do we have formulas for the conditional, let's say, of xa given xb? All right, that's exactly what I'm going to do. And actually, I have the equations that you need to use in the slides for a multivariate Gaussian. So effectively, what I need to do is, if I partition things like that, I need to find, you know, what is the probability of x of the distribution of xa given xb. So if you do the algebra, there is the answer. All right? So where is the answer? Do you see it? Give me the final answer. So this distribution comes to be a Gaussian, all right? And that has this mean that you see here. There's no miracles here. You just plug in the generic formulas that we have seen for multivariate Gaussians. So this is the mean, okay? And the variance comes to be C minus K transpose C and inverse times K. Okay? So somehow we have now the ability for any new input point to produce the probability of the observations, if you like. It's a predictive distribution. And in some sense, because xn plus 1 is arbitrary, literally what we have derived here is what is called a posterior Gaussian process. Because in essence, here I wrote you the calculation for this, the probability of Tn plus 1 given the bold T. But I can actually, instead of giving you the probability at one point xn plus 1, I can give you the probability of the observations at any arbitrary other set of points, right? Because the whole thing is a Gaussian process, so I can actually compute the probability of observations at any set of inputs, all right? Condition on my previous data, all right? So in principle, this defines what we call a posterior Gaussian process. Now, if you, not that we have to follow that avenue, but if you sort of go in and take this vector here, and you define it as alpha, the n component of that, we define it as the n component of a vector A, you can actually write the mean as, so we're looking at the point xn plus 1, and we can write the mean as the summation of this components an times the kernel evaluated at xn plus 1 and at each of the training points xn. So if you actually imagine, if you look at this equation, you know what the mean looks like? It's like, it looks like a radial basis function model where somehow you put a basis, if you like, at every training point xn, and the basis here is really a kernel, all right? And then you actually take an averaging of the observations at each of the training data points. I mean, these observations, of course, they are given by this formula here, but in essence, this has similarities with a radial basis function model, but certainly we don't want to follow that idea, right? We want to be way more general. And I want you to understand here, this is what you will do when you program things, right? You will say, give me the predictive distribution at a new input point, and you say this is the mean and this is the variance. But the idea is because originally we assume a Gaussian process as the prior over these regression functions, I can actually take any combination of new input points and the distribution will still be Gaussian given by similar formulas. Okay? At arbitrary input points, basically, and of course it's called a posterior GP because I use some training data T, and I started with some prior on the type of functions that we're looking at this particular problem. I don't know if this picture will tell you anything. I think it's from Bishop's book. If you think, you know, this is the joint distributions of two observations, and this is what we started to do the derivation. And you notice if you conditioning T2 on T1, you will get a Gaussian distribution. So to do predictions, we have to do conditioning on, in essence, on an infinite dimensional Gaussian, all right? And so we will always be getting everything to be represented as a multivariate Gaussian at the end of the day. All right. So how does this, so we have this formula for predictions, and the question is, how do things look like actually when we try to plot them, okay? So let me just remind you, this distribution, if this is a scalar, all right, has a mean that is given by this formula. Cn is, remember, is defined in terms of the kernel metrics at the end training point, and then we have this vector k and this variance. So all the things we can compute them, and if you remember, this is in essence at any point xn plus 1. So in essence, I can actually plot this as a function of xn plus 1, all right? So if you do that, you will get a plot that looks like this. So what you have here is this function that you see here is what generated the data, the training data with some noise. And this line on the middle is actually the mean of the predictive distribution that we get. Okay, so it's the mean of the predictive distribution. And this, what you see here, is plus minus 1 standard deviation. Okay? Literally, I mean, this is what the major concept of Gaussian processes is, right? That it allows us to write a predictive distribution, and here is, we did this in 1D, that is a Gaussian, but the key ingredient here is that if you take the joint distribution of the predictions at any arbitrary set of points, any axis, the distribution is Gaussian, okay? All right, and so here you see a plot of the predicted distribution for a scalar value of x. Okay, don't need this, already discussed it. Okay, so this is another example, okay? And actually this example involves fitting a square exponential kernel with, so these are the stars that you see are the training data points. So you start with some values of the parameters of the kernel, you don't know what to do, and obviously you're gonna do some optimization to maximize the marginal likelihood, the evidence, and when you maximize the evidence and you recompute the parameters, the prediction will go from something that looks like uniform, something that, you know, here looks like the only thing you get is the noise level beta that we had in the likelihood, to get to something that is a little bit more sophisticated and more correct. And you know why I say this is more correct? Because you notice if you're away from the data, the noise gets higher, right? Here, you notice some areas away from the data, the noise seems to be the same as where you have lots of data. That doesn't make lots of sense. But once the system is trained, basically, this is what you get with the correct hyperparameters for this problem. Okay, so here's the formula I was telling you. If you have trained a GP for some inputs x and you have some observations t, okay, this is the posterior GP evaluated at an arbitrary set of points x star. So this is not just at one point, but a vector of input points x star that you see here. And it has a mean that is given by this nice equation, and a covariance that's given by this nice equation. Okay? And just for the notation to be clear, when you have something like that, right, so k star is evaluated for the inputs x star and x star. You notice this k here is evaluated for inputs x star and the training inputs x, okay? And you can also appreciate the cost of the computation involved here. You're going to have to do this inversion of this matrix. What is the size of the matrix here that you are going to have to invert? If you have n training points. How much? It's n by n, right? So if you try to invert n by n without any sophistication, basically the cost of this inversion will be n cubed. And I remind you, when you use finite basis functions, right, and you have n of those, the cost of inversion for regression problems is n cubed, okay? So if n is very big here, you're not going to be able to do it. And that's a limitation of Gaussian processes. And obviously, if we had the whole course available, we'll discuss about sparse Gaussian processes and doing this trick and doing that trick. the bottom line is you can do lots of things, but you will have to use tricks applicable to particular functions to make this to work, okay? In general, you are doomed basically because lots of the approximations that you can do for this, even if they look nice, at the end of the day may not work for when you have lots of training data. Okay, and all right, so that's another nice plot, and again, you can see how narrow the posterior uncertainty is when you have lots of data, and then when you have no data, you can see immediately the uncertainties get very big, okay? This is very simple to actually plot, right? Because you have the analytical formulas for the predicted distribution with the error bars for every x. So you basically have to evaluate them and then just smooth the discrete values that you got. But beyond that, right, in principle, we get this calculation by evaluating this at distinct points. But really, I want you to think that actually what we get is we get these functions that you see here. Because the calculations we do them by sampling arbitrary points. So I can actually, it's not like you plot this and you say, I'm going to calculate at minus 1.5, minus 1, minus 0.5. You're actually, you can evaluate this at any point, continuously, because these functions that you see, they are not made by taking discrete values and connecting them with straight lines. They're real functions. All right, so this is basically values that you get from the posterior GP, okay? I mean, one thing is how you evaluate them and how you plot them, right? But the fact is, what you're producing is you're producing a posterior distribution over functions, okay? A posterior distribution over functions because you have basically the way to evaluate this, this distribution at arbitrary input points. Okay, I mentioned before that somehow you would, because you will have to invert this, you remember when we talked about the prior GP, the only covariance metrics we had to involve it was the kernel metrics. In the posterior GP, actually, you will notice the metrics that we get is the kernel metrics plus this diagonal noise. So in essence, even if this thing here is singular and you cannot invert it, when you add this small noise in the diagonal, then the whole thing becomes invertible. The idea here is, even if you don't have beta, add a little bit of beta there as a way to stabilize and allow yourself to do the inversion of this covariance metric C. Okay. I'm not going to do this the following derivation, right? But let me just say, so I derive the posterior Gaussian process for this. You can actually take the calculations that we did for the mean and the covariance, and where you have kernels, start substituting the kernels with the equivalent basis function representation. And if you do that, you will actually discover everything we did early on in the course for regression in terms of basis functions, okay? So there is an equivalence there, but the idea here is when you start directly with kernel, in principle you have infinite basis functions, right? In principle you have infinite basis functions. So you don't need to have a representation in terms of a phi of x the way we did earlier in the course. Okay, so I'm going to bypass this. So let me, I want to at least have 15 minutes to do the classification using GPs because it has a particular level of complexity. So let me go rapidly through some of the slides. First, learning the hyperparameters. So we need to maximize this evidence. The evidence involves this metric Cn. So you notice this is a Gaussian, right? So you will get this from the quadratic of the Gaussian, and you will get those two terms from the normalization. So as you can see, Inside here, you have the kernel hyperparameters, and of course the noise is also unknown. So you need to be able to calculate derivatives of the log of determinants, and also you need to calculate derivatives of the covariance matrix inverse. Okay? So, effectively, I give you the formulas that you will need. If you want to differentiate the inverse of a matrix, right, you can see here, there is an inverse of a matrix. You will, this is a simple calculation of the gradient, okay? And if you want to find the derivative with respect to an argument of a log of a determinant, it's basically trace of a minus 1 del a del x. The derivation is basically straightforward for all of this. It follows basically some spectral analysis, writing things in terms of the eigenvalues and eigenvectors of the matrix A, but these are the only computations you need, and so you can use your favorite optimization method to actually compute the hyperparameters that you see here. One note of caution, don't get the impression that in general, training this Gaussian process and computing the hyperparameters is a trivial task. So when you play with the software that I gave you, and you try to change the setting even on these sample problems they have, you will see you start slightly from a different value of parameters, and the algorithm doesn't converge. Okay, so this is there is a little bit of art there to make these things to work. Okay. And something else about, since we talk about computing the hyperparameters, so if you have a high dimensional input, the question always is, right, that's what when we discuss about sparse models, do you need all these input variables? Do they affect actually the observations? So what I'm having here is, I'm having a kernel defined of, in the context of what's called automatic relevance determination that we have seen before. So I mean, basically these are the inverse of the length scales, but if you put it in this form, you can actually maximize the evidence and compute this parameter theta I, and can you guess what that will mean in the context of automatic relevance detection? I mean, if you, let's say you try to find the parameter theta that maximize the evidence, what can you say if one eta comes to be equal to 0? Or very small versus the other etas? Means that that direction, right, that dimension in your input is not very important, okay? So you can actually get rid of it. So there is an example that there is in the notes, and you can run the MATLAB code on this. It has it's an artificial data set where somehow the observations don't depend on the third dimension at all. And when you optimize the marginal likelihood, indeed what you get is that eta 3 goes to 0, and the third dimension is unimportant. So everything you learned about automatic relevance determination, you can do this by using kernels that have this form, where the length scales are being computed, right? So you compute the length scales. So when you find that the inverse of a length scale is very small, you can actually get rid of that particular dimension because it does not affect your observations. Okay. I don't have to tell you this, right? But you know, if Gaussian processes are basically used as surrogate models in high dimensions, these days everybody does Gaussian processes. Okay, even if we don't really understand what the Gaussian process is, because it's very simple to implement. It's the most trivial probabilistic model for doing surrogate modeling. So you can use it for doing inverse modeling. You can use this for uncertainty quantification, for optimization, design, and all the likes. Okay. What are the challenges when it comes to recent research? And there's a lot of people who work on this area. We already mentioned if you have a large training data set, basically the classical techniques don't work because you have to invert an n by n matrix. So that's where ideas of sparse Gaussian processes come to play a role. The majority of those sparse Gaussian processes don't always work, okay? Second difficulty is when you have high dimensions, these methods are sort of in a murky territory because these kernels are based on the sort of a notion of a distance, and distance in high dimension can mean different things. So lots of techniques don't, a lot of GP implementations don't work in high dimensions. And then we already saw that if you have variability that is different in different directions of your input space, so you have non-stationarity, again, training the system to learn the length scales is also a very difficult task. Okay, so let me just go, I'm going to spend 5 minutes to tell you a little bit about GP kernels and what's out there, and then I'm going to move directly to classification. The definition of the kernels we already have seen actually what is an acceptable kernel. We had a special lecture on kernel functions. So effectively, we require that these kernels are positive semi-definite, okay, in a formal definition that you see here. You may want to know the idea of a kernel that is stationary. Stationary means it depends on only the distance between x and x prime. So this type of kernels are, you can imagine that you you move this, x by some distance c, and x prime by the same distance c. So this will be an invariant to translations. You can simplify the kernels further, and you can make them isotropic, where the orientations don't come to play at all. It's only the Euclidean distance between x and x prime. And so here you get an invariance both in translation and rotation. You can show under certain conditions that the Gaussian processes satisfy continuity. Continuity, because Gaussian processes are distributions over functions, the only way you can talk about continuity is in the mean square sense, all right? So you cannot say, oh, these functions I get are continuous. Well, these are realizations of functions from a probability space, so you need to use mean square continuity defined that you see here. You can read more on this in the slides. You can actually, you may ask, can I differentiate if a Gaussian process, a distribution over function, can I actually differentiate those functions? And to be able to differentiate the Gaussian process in the mean square sense, again, the kernel, the second derivative of the kernel needs to exist and be finite. This is interesting. And actually, if you are interested on this aspect, you can think, if you actually have samples, let's say if you have a kernel that is differentiable, and so you have the gradients of a GP that they are also GPs, you may ask yourselves, can I take samples from the gradient of a GP and use those samples together with samples from the GP to do estimation, right? Because they're all coming from the same underlying kernel. And the answer is yes, and there is some work done these days in this direction. We do not see much variety on kernels. This is the Matern Covariance kernel, extremely important, okay? There's a lot of fine details here. I'm just clicking so you can get a sense of the type of functions that you get from a GP prior based on a Matern covariance. This is a a rational quadratic covariance. Alpha is any arbitrary positive number here, and the functions look like that. This is a kernel that allows you to model periodic functions, right? So in your kernels, you want to put any information you have about the type of functions you want to model. So you can actually, if you want to model periodic functions, there are kernels that allow you to embed this information. So the prior functions that you get are periodic, okay? And everything we learned on when we discuss about kernels is applicable obviously to Gaussian processes. So if you have two valid kernels leading to two covariance functions, you can add them up and you get a valid covariance function. You can take product, you can take direct sums, you can do convolution, you can actually do tensor products, you can pass through these kernels to arbitrary functions and you get valid kernels. You can do anything you want to, and there is a lot of research actually on doing this type of transformations because they may allow you to embed particulars of your functions that otherwise you will not be able to model. And I'm going to give you one example. If you have a function in high dimensions that somehow you can decompose to one body effect, right? So this is, all these terms involve only one variable at a time. Here is two body interactions, three body interactions. So this is what's called, high dimensional model representation or ANOVA expansion. So if you have a function that is like that, okay, then actually, if each of these functions are coming from GPs with kernels ki that you see here, xi prime, and this comes from a kernel kij, etc., then this function f of x comes from a kernel that follows the same ANOVA decomposition as the functions. This is extremely important, and only actually literally the last maybe 3-4 years, people have started taking advantage of this type of idea. So, if you have a high dimensional function, maybe, rather than looking for arbitrary kernel, maybe you say, I'm going to use a simple decomposition that looks like this, where I sum basically the contribution of individual kernels in every direction. And I think there is, so here is sort of a picture where, actually let me see. Okay, so let me go directly to this picture. Here is sort of having first order interactions from 3 kernels, then having second order interactions, then having third order interactions, and then having an additive kernel of all 3 possible interactions. So you can model things as simple as this, or you can add now second order effects, third order effects, etc. And here is one example of a function that involves 2 signs. So there is obviously, you can, if I give you data, right, that coming from this function, and I tell you go and find me a Gaussian process to model this, you will not know that I have 2 additive effects, one a function in x1 dimension and another function in x2 dimension. R defines the periodicity here, okay? So I give you data so you don't know the structure. So let's see what happens. So if this is how the true function looks for r equal to 2, this is if you try to model with 1s for exponential kernel, and here is how what you get if you use the ANOVA expansion, where you add kernels independently in each of the 2 dimensions, okay? So you can see this is way better representation of the true scenario than using a square exponential kernel. And if you use r equal to 4, so you increase the periodic cells, you can see again having only this one body terms allow you to model this way better than using a square exponential kernel. Of course, you may say, okay, this is better, but how will I know what interactions do I need on my problem if I have no idea that I'm adding two signs, right, in x1 and x2. Well, yes, I know, that's a problem, all right? But somehow you can think, maybe you start with an ANOVA expansion, and maybe you don't have to include all two terms. Maybe you include one body terms and two body terms, and maybe in high dimensions, not all of these terms, because maybe you can do relevance determination and decide which of these terms are needed and which they are not. But somehow, if you allow for a kernel decomposition that looks like this, and you put length scales in each of these kernels, you can figure out, based on the training data that you have, which terms you need to keep, okay? Because don't get the impression, I mean, if it's a problem in 10 dimensions, this decomposition will give you thousands of components that you need to account for. All right, so let me highlight very fast the difficulties on using Gaussian process for classification. And if nothing else, it's sort of a very good exercise on manipulating Gaussian processes. Okay, so you should look at it. So what's the idea, right? So you can think of, we're trying to, we have two classes, and we have training data for class 0 and class 1, all right? So we really need to produce, given some training data, we need to produce the posterior distribution that X, let's say, belongs to class 1. So we need to have the posterior probability that T is equal to 1, given some training labels of points where we specify what class each point belongs with no error. So the idea is extremely simple. The implementation is difficult. So the idea is, how about if you put a prior, you create some Gaussian process on, for the input X, and I call this Gaussian process here prior A of X. And A of X will give you samples like this weird function that looks like that. This doesn't look like a probability from 0 to 1, but what you can do is you can take this weird function, pass it through a sigmoid, and then basically squeeze it from 0 to 1. That's exactly what we will do. We will model, we will start with some GP priors that look like GP prior that gives you functions like this, pass it through a sigmoid, and this together will give us basically the probability that this point X belongs to class 1. Okay? So we're going to model the distribution. So given A, remember A is a function of X here, given A, all right? The probability of T is going to be a Bernoulli distribution. So with probability sigma of A, I belong to class 1, and probability 1 minus sigma A to class 0. All right, so this is a Bernoulli distribution. So the algebra is trivial, all right? So I give you some training data set. I tell you here is the inputs x1 to xn, and this belongs to class T1, class Tn, where these labels are 0 or 1. So this is the training data. And here is what we need to do is, we need to calculate this. We need to know a new point xn plus 1, we need to know to what class it belongs. So we need to produce a model for the probability of Tn plus 1 given the training data T. So remember, this is the objective, right? Once we do this, we're done, okay? Remember, we start with a Gaussian model for A. So if I have n plus 1 points, remember my training involves only n points, but I have an n plus 1 point to do a prediction there. Will you agree with me, because this follows a Gaussian process, that this equation is valid? You remember for Gaussian processes, right? Okay. Remember, this is a vector, involves a1 to an, but also involves an plus 1. So that's a Gaussian process. Okay. And this is what we need to produce. All right. This is what we need to produce. So this is the calculation. We need to compute the posterior probability that Tn plus 1 is equal to 1 given my training data Tn. So what I do is I plug in an an plus 1 in the argument, and I integrate an plus 1 out. And I write this as using simplifications of this joint probability as the probability of Tn plus 1 given an plus 1 times the probability of an plus 1 given Tn times dan plus 1, and I integrate an plus 1 out. Do I know what this is? Yeah, by definition, that's my sigmoid function. All right? You remember this is a Bernoulli distribution, so this is the sigmoid function. So what I really, to compute what I need, which is the probability of Tn plus 1 given Tn, I need to be able to compute this integral. And to compute that integral, we need to evaluate this probability. It comes out, all right, that this distribution is not Gaussian. So to simplify, we are going to make it Gaussian, because you may remember this. If you have to integrate a sigmoid with a Gaussian, do we have an approximation for that? We have seen this when we discuss about logistic regression. You remember an approximation when you have to integrate a sigmoid with a Gaussian? The answer is yes. There is a nearly exact formula. It's an approximation, but it's very good. But if you integrate the sigmoid with a Gaussian, you can write this directly as the sigmoid evaluated for k given by this nice formula. So the idea is to be able to finish the result and come up with a nice approximation of this. Okay, we will need to make this a Gaussian. And to make this a Gaussian, what do we need to do? How do we take an arbitrary distribution and we hope that the Gaussian approximation will be valid? How do we call that Gaussian approximation? Laplace approximation. So 137, so I can concentrate on the blue formulas. So remember, this is what we need to approximate now with a Gaussian. And it comes out, this is equal to this nice integral. Okay? And look at the first term. Do we know P of an plus 1 given the vector A capital N? Do we know that? And from where? So this comes to be equal to that, right? So do we know that first term? From where? Remember, what is A? A is a Gaussian process, right? So this is the posterior of the Gaussian process. I can, given an, the distribution of an plus 1 is a Gaussian. Here's the answer. We had it before. All right? So that's a Gaussian. Now, the question then is, we have a problem because you remember T is defined through a sigmoid. This is a Gaussian process, so the probability of an given Tn, it doesn't look to be a Gaussian. Okay? So, so let's see what we're going to do this. So if you write this in an unnormalized form as the probability of Tn given an times the probability of P of an, it comes out, all right, that this unnormalized probability can be written down with this prior, which is the evidence basically from the Gaussian process that we had, and this thing that comes from the Bernoulli distribution. And if you take logs, all right, it comes out that the log of this distribution we want to compute looks like this. Okay, how do you do Laplace approximation? Remind me of, so if you have a distribution, how do you do Laplace approximation? What ingredients do we need? What do we need to have an approximation of something as a Laplace approximation? We're going to fit a Gaussian, right? So what do we need? We will need to find the mode, and then we will need to find the Hessian, the second derivative on the mode. Okay? So effectively, the log of that distribution looks like this. So we will need to find the first derivative, set it to 0 to find the mode. And the bad news will be when you set to 0, the formula can only be solved iteratively. That's one thing. And when you compute the Hessian, it comes out that also the Hessian will require an iterative type of calculation. And is this a big deal? No, because to compute actually the mode and the Hessian at the mode, what you can do is you can use the iteratively weighted least squares algorithm, right? You can use a Newton's algorithm. I mean, this is what basically you can think here, that AN plus 1 would be AN minus 1 over the Hessian times the gradient, and you start iterating on AN. When it converges, it will actually give you the mode, and for the mode, it will give you the Hessian, and then you have a Laplace approximation, and the Laplace approximation will look like a nice formula like this, okay? And if you have that nice formula, you plug it in back in there, and you're done. I mean, at the end of the day, somehow you have an integral of a sigmoid with a Gaussian, and A1 plus 1 integrated out, and there is an exact, almost exact formula of that in terms of a sigmoid with some scaling k, and so you're done, all right? So you have a posterior distribution of Tn plus 1 being plus 1, given the training data. The question now is, okay, we have all of these nice things, we can do predictions, but how do we train the system? If I give you n data points, right, with labels, how do you compute the hyperparameters, you know, the kernel parameters? How do you do this? For classification, that's always a difficult problem, okay? Not just in this context, but in general, it's a difficult problem. So to be able to do this for classification, you will need to compute the evidence, right? This is what we had before. And I'm using here a Laplace approximation for the evidence. You can think of this sort of as a Taylor series expansion. I see there is psi at the mode, and the first derivative is missing because it's 0, and the second order term. But anyways, you will have to find the gradients of this model evidence with respect to the hyperparameters. It's tricky, involves a lot of terms where the hyperparameters are hidden. If you do them carefully, and I have grouped them in the slides, all right? So operating on these three terms, computing directly terms in terms of derivatives with respect to the hyperparameters, and there are some other weird terms that they depend on the hyperparameters through the alphas. When you work out the algebra, you have basically everything in terms, you have all these gradients of the evidence with respect to the hyperparameters, and you can use your favorite stochastic optimization algorithm to update the parameters, and and use this together with the predictive distribution, and you can compute effectively the posterior probabilities. You know, these are colored base probabilities of being to class 1 versus class 0. You can find the separating hyperplane basically with that's the curve is where the posterior probability becomes 0.5. Okay. Again, this software, Matlab, is actually one of the early softwares used for stochastic optimization, coming out of Bishop's group at Microsoft Research. So you can actually download it for free if you are interested. It has a lot of the data sets and the algorithms for implementing this problem. One final note, we have only 1 minute. For those who work on Bayesian neural networks, in a sense, neural networks have a lot of implicit layers defined in terms of parameters W. So if you put a prior on those parameters W, in essence, you're getting a distribution over functions, okay? So it comes out that this distribution over functions in the limit of this hidden leg going to infinity becomes actually a Gaussian process. And if you're interested to do this, I don't know why I don't have it here. Okay, here it is. If you look, actually, what the book on the bottom is the PhD thesis of Neil, out, I think, of the University of Toronto, where basically he formally proved the connection between neural networks and Gaussian processes. He actually, in his thesis, he showed that if the hidden units are, the activation functions are Gaussian, you can actually derive analytically the kernels, but it comes out that the kernels are non-stationary, okay? And they are non-stationary because effectively the prior use over the weights, they are Gaussians centered around 0, so they don't satisfy translation invariance. And so there's interesting aspects of this, but somehow GPs and neural networks on the limit of m going to infinity lead to the same thing, okay? So this is another nice paper that discusses about this aspect. Okay, so we will have some student presentations on Thursday, okay? And I'm still looking for another volunteer. Okay? You volunteer, you said? No? All right, extra bonus.